So thanks everybody for coming today. This is a terrible way to start, but I actually have a correction. So we just recently changed the name of our department. It's now the Department of Biostatistics, Epidemiology, and Informatics. So this is a very new group. There's no actual graduate program in informatics at this stage, but forthcoming if any of you are interested. So I wanted to spend just a few minutes talking about the biostatistics program primarily at Penn and a little bit on the EPI program, since Peter said that some of you might be interested in pursuing graduate work in biostat and maybe EPI. And then the majority of the time today will be spent on a little bit for my research. So for those of you who maybe aren't familiar with biostatistics, it is the science of the design and analysis of biomedical research studies. So what does that mean and what do we do? Well, basically I work collaboratively to design scientific studies and analyze data generated as part of biomedical research. So this includes clinical trials, observational studies, large health database studies, and human genetic studies. Some other things that we do is develop new theory, methodology, and analytic methods to address complexities that arise from data obtained through biomedical research. And probably one of the most important things that I do is ensure that existing statistical methods are used appropriately to analyze data arising from different kinds of research studies. At Penn, we offer 2 degree programs. There's a master's degree and a PhD program in biostatistics, where the goal is really to train you in the theory of biostatistics and in the application of statistical methods. The PhD program also goes on to train students to become independent researchers, and you do this through actually developing a new method to address some kind of problem in biomedical research, and that's done through your dissertation. The timeline for the PhD is obviously much longer than the master's degree. Usually it takes 4 to 5 years. Typically your first 2 years are almost exclusively coursework. Then you have to successfully go through a qualifying exam, which has 2 parts, and then there's a candidacy exam, which is what actually allows you to officially become a PhD student. And then the culmination of this work results in a doctoral dissertation, which you have to defend before successfully getting the nice piece of paper that says PhD on it. The MS degree only requires mostly coursework. Again, that takes roughly 2 years. There's a lot of overlap between the coursework for the 2 degrees. And at the end, you'll need to also successfully go through a qualifying exam, which is at the end of your first year, and you'll have a master's thesis that does not require defense. You just need to hand it in. So for the PhD students, this would be your typical timeline. So in the first year, you'll take courses. You'll do something called a lab rotation, which I'll talk about in a second. And then at the end of the first year, you have 2 qualifying exams, an applied and a methods exam. And then in the second year, more courses, more lab rotations. You'll do a consulting seminar. And then at this stage, you'll select your research advisor and hopefully start to develop your actual research area. And then at this stage, you'll also need to come up with a funding plan. So usually that is purely based on who you're working with. They'll usually fund you through your dissertation, but sometimes that might require writing a grant to the NIH, for instance, to get a graduate grant. And then in the third year, you'll do your candidacy exam, which is basically presenting your proposed dissertation topics to your committee. And hopefully they say, yes, if you do this, we'll give you a PhD. And then you can actually continue on into your research. And then basically after you do that, all that's left for you to do is to actually write your dissertation. And then throughout all of this, you might also act as a teaching assistant to help fund your time at Penn. If you were going through the master's program, your first 2 years would look almost identical, except that you wouldn't have this selection of a research advisor and development of the funding plan. In your second year, you would instead be working on your master's thesis. So we have a lot of coursework, a lot of courses, I should say, that are being offered at Penn, as well as several reading groups. In terms of courses, there's things like probability theory, statistical theory of inference. We have linear models and generalized linear models. There's survival analysis, study design. We have computing. Like I said, we have a consulting requirement as well. those comprise generally the core courses that we require students to take, and then we also have a bunch of advanced electives, so this could be like Bayesian methods, statistical genetics, causal inference. I hope one day to be offering a spatial statistics class, but that hasn't happened yet. The nice thing about being in Penn Biostat is that you also have the opportunity to take classes through the Wharton Statistics program, and they have a lot of really interesting stat theory classes like measure theory, stochastic processes, machine learning, and high-dimensional data analysis. And in terms of reading groups, we have topics such as causal inference, semi-parametrics, empirical processes, imaging, which is a really big, fun one right now, clinical trials, and genetics. So we cover a very wide range of topics that should hopefully, there should be something interesting there for everybody. So now going back to the lab rotation idea. So this is fairly new at Penn and I think unique to the Penn Biostat group. And the goal of the lab rotations is to expose students to biomedical research as early as possible in their career. And particularly we're focusing on statistical methodology training rather than applied training. So the idea is that when you enter into the program, you rotate through a number of different labs, which in this case are just faculty members, in order to get a broad perspective on research. So you'll get a feeling for working, what it's like to work with different faculty members to see if your styles mesh, but then you also get exposed to different areas of research, some that you might not have even heard about before coming to Penn. So you go through this process of 3 lab rotations or so a year over the first 21 months of study. And the goal is that by the end of your second year, you would have already started working on your dissertation topic and also have identified an advisor. And so the nice thing about going through this lab rotation is that we're hoping people can get into research much earlier, which will cut down on the total time needed to complete the PhD. And again, this is unique to Penn and still new for us. And another bonus is that the students get to choose the lab rotations. So this is not something that the faculty or the department imposes on you. You choose every semester which person you want to work with. And the way that that works is that each semester at the very beginning, any faculty member that has a project will present it, give like a little 5-minute sort of sales pitch. And any student who's interested in pursuing that project meets with the faculty members, and then after that process, there is a matching procedure where students and faculty get paired up to work together. In terms of financial support, all of our full-time PhD students are fully funded for up to 5 years, sometimes longer depending on the sources of funding. And what that means is that we pay for your tuition, all fees, and all healthcare, and we also provide you with a stipend. So I'm not really sure what the stipend is at now, but I think it's around $35,000 for a year. So it's not nothing. And then there's also training grants that are available to fund US citizens or permanent residents. So training grants basically require you to specialize in a certain applied area of interest. The training grants that we have at Penn are in mental health, cancer, renal disease, and genetics. And unfortunately at this time we don't have any guaranteed funding for those in the master's program, but there are ways to sort of help offset the cost of your studies, and that's through like research assistant positions, TA-ships, and things like that. So just to brag about some of our students who graduated from the program and where they've gone off to. So we have many students going into academia, government, and most of them I think end up in industry. In terms of academia, they end up either in tenure track positions or in instructor or postdoc positions at a variety of prestigious universities, such as at Harvard, University of Washington, Temple, Brown, Pitt, Carnegie Mellon. And you're not necessarily restricted to be in a biostat or stat department after you graduate. Computer science, dentistry, oncology, pharmacology, a lot of these departments require biostatisticians, and some of them will hire them in-house in their department rather than, say, working with somebody who lives in the biostat program. In terms of government positions, people have gone on to work for the NIH and different branches within the NIH, the FDA, and in the VA as well. And some examples of industry positions are at Amgen, Johnson & Johnson, Merck, and Pfizer. So why should you consider UPenn in general? Well, we have an outstanding school of medicine. We're currently #2 in terms of NIH funding. Number 1 sits at Harvard, and number 3 is at Hopkins. Given the current political climate and the cuts that are being made to NIH, this might become increasingly important in the years to come because reputation might stand for a lot of whether or not people get funded, unfortunately. We are a prominent Ivy League university. We are supposedly the nation's first university, the first medical school, the first business school, and we have the first modern liberal arts curriculum. We have a lot of high-profile medical research going on that's published in top journals, and it's frequently featured in national and international news. We have a somewhat compact campus which promotes multidisciplinary research, because as I'm sure you guys know even here, people are housed all across campus and you need to be able to meet with people face-to-face in order to have productive collaborations. And there's just a lot of outstanding intellectual research and talks going on many fronts, so there's many opportunities to learn from many different people. In terms of our department in particular, so the Division of Biostatistics has currently 37 faculty members with between 0 and over 40 years of experience. We all come from a wide range of graduate schools, including Harvard, Columbia, Yale, Hopkins, a few others. UW is another big one, Penn State, UCLA. That brings a lot of diversity into how we teach our students, how we mentor our students, and how we perform research. We cover a variety of areas of expertise listed here. Some of the big groups are causal inference, genetics and genomics, and longitudinal data methods, so that's when you're following people over time. And then I'm going to plug mine. So I do some Bayesian modeling, which you guys probably have not heard of. So that just means you take into account information that you might already know about variables into your modeling approach. And the big one here is the spatial analyses, which is why I was recruited to work at Penn. Yep?
Is the 40 plus experience, that's the range that experience each individual has? Or?
Each faculty member, yeah. Yeah. So another benefit of going to Penn is our extremely low student to faculty ratio. So what that means for you is that you get a lot of personalized attention and there's less competition for finding a dissertation advisor. It means the faculty are really available to help their students. So some of the other bigger programs you can see, especially University of Washington, where Peter and I graduated from, there's a lot of students in the department, so it creates a sort of competitive environment in order to find an advisor. For those of you who might be interested in pursuing a graduate degree in epidemiology, we also have a division of epidemiology within the department, which is quite large. There's over 60 faculty members in the epi division, but most are actually primary in other departments. So there's really only, I think, 7 faculty members who have a PhD in epidemiology, and the remainder are primarily clinicians. So these are MDs who are practicing, still seeing patients, but they have masters of clinical epidemiology, or MSCE degrees, which allows them to perform research as well. So their primary homes are in their clinical departments, and their secondary home is at EPI. So you can imagine what faculty meetings for the department look like with about 100 people who try to show up. Okay, so the programs of study that are available through the EPI department are the MSCE program and the PhD program. So the MSCE is an intensive program really aimed to train accomplished medical professionals. So 99% of the time, these are MDs who want to conduct research on the side. They're learning to design controlled EPI studies and acquire baby biostat skills to help them get their research moving forward. I think really the goal here is to get them to recognize how important and complicated biostats can be so that we can work together to advance their research agenda. Penn also has a very small EPI PhD program. Currently, they're only enrolling about 1 student per year. They are working on making this a bigger program, so maybe in 3 or 4 years they'll be enrolling more, but it's very, very small right now. So the caveat to the PhD program in EPI is that all of the classes overlap with the MSCE program. So what that means is that they're at a slightly lower level, it's much more applied. And so I think that the training is very different for the EPI PhD at Penn than at other programs. Again, you're looking at a 4 to 5 year timeline with roughly 6 semesters of coursework. And then the rest of the time is devoted to your dissertation research. And so even though it's 6 semesters of coursework, it's really just 2 years of intense coursework. And the next 2 semesters after that are more like graduate seminars, dissertation seminars, grant writing, and things like that. So less about actual courses. So if you're interested to learn more, you can feel free, first of all, to email me, and I'm happy to field any questions or direct you to somebody else who might be more appropriate to answer your questions. A fantastic resources for the graduate's work in Biostat or in Epi is our graduate program administrative manager, Catherine Vallejo, whose email is given there. You can also look at our departmental website, and then I've also listed here the specific websites for our graduate programs, both in Biostat and in Epi. Is there any questions that I can answer immediately about the program? So? Okay. So let's switch gears to talking about some research. So I work in a number of different areas. I have a secondary appointment at the Children's Hospital of Philadelphia, which means most of my applied work is actually in pediatrics. So that sort of ties into the talk today. And this is just one of several interesting projects that I am working on right now. So I had a really hard time picking what to talk about, but I think this has a really interesting real-world application, so hopefully you can understand the motivation, even if some of the statistics behind what I'm doing are a little bit vague. Okay, so what are we talking about today? So what I would like to talk to you about is the importance of civil registration. So in most of the developed world, the US included, where we get public health information comes from a civil registration. So what is the point of the civil registration? Well, it serves its purpose to create a legal record for each person, and that really ensures that the civil rights of people are maintained. But what's happened over time is that we use the civil register in order to get vital statistics about people in the population. So what are vital statistics? Well, that's things like birth rates, and that can be stratified by age of the mother, mortality rates by different covariates like sex and age, or causes of death. So when you hear things like the leading cause of deaths among women aged 40 to 50 is whatever, that's a vital statistic, and it comes from the civil registration that exists in the US. So this seems like a pretty simple idea, right? You can just record when everybody is born, follow them through time, and there's ways to tie people together, so what's the big deal, right? Well, the problem is that this is actually really expensive. It's very expensive to maintain, and it's not really easy to keep it going in a useful fashion. So in places like the US and Canada, it's not a big deal because the infrastructure is there, they have money to maintain it and people to maintain it. People are easily attainable because everybody has phones, a lot of people have computers, email, things like that. But the problem in low to middle income countries is that there is not the funding to do that, and because these systems are already in place, it would take a massive amount of effort in order to set something like this up. So what exists currently in low and middle income countries is that you have basically nothing, or you have something very little, so maybe in the more populated areas, or areas that might even be considered more urban rather than rural. So if you look through the literature involved in studying civil registration, many will argue that full coverage civil registration is the only thing that matters to ensure civil rights and provide each unique citizen with a legal identity. Nobody can argue with that. That is absolutely true. But that should be the long-term goal, because we don't actually need full coverage civil registration in order to get useful vital statistics, because we have sampling available to us. And if you've all taken Peter's statistics class, hopefully you guys have talked about sampling. So sampling is super, super important. We have a lot of effective and very efficient methods for sampling, and from statistics we know that we can use sample data to make inferences about whole populations. So from an information point of view, it's not necessary to have data describing every vital event and each unique citizen. In fact, from a fiscal point of view, it is actually somewhat irresponsible to insist on having this full civil register, because you don't actually need it to get the vital statistics, which is really what people want. So why is that important? Well, what happens is that in places like or in different countries of Africa, say, where you have an Ebola outbreak, you don't really have a baseline population with which you can say, okay, how many people, like what proportion are actually being affected? Because you don't really know who's there. There's so many people like existing behind the scenes. And so subsequently, when people go in and try to implement some kind of intervention, they have no idea how well they're doing because they have nothing to compare it back to. Okay, so what have some places done in order to circumvent this problem? Most places are just going to implement some kind of survey. So they'll send a survey to your house and they'll say, okay, can you please answer the following questions for everybody that lives in your household? And so they'll do this several times over several years, and that's fine, and they'll get a nice picture of what might be going on in the country. But the problem is that it lacks ongoing prospective, the longitudinal structure of a traditional vital registration system. And so what that means is that they can't easily measure trends and changes very well. And the reason for that is because they're not actually following your household or my household every single time they're sending out the survey. They're sending maybe my household 1 year and then Peter's household the next year, and the year after that maybe they reach out to Lisa's house. So it's not the same people being followed every single time. They often lack spatial resolution to distinguish differences in indicator values across short distances. And basically what that means is that because the surveys are being taken sporadically, say across an entire country, you might end up with pockets that have absolutely no information at all. So if you wanted to say something about a census tract in the US, for instance, you might not have anybody represented in a bunch of census tracts. So the best you might be able to do is make conclusions at the county or even the state level. And then because household surveys are only being sent out to usually a random sample of people, they're not being sent out to very many people at the same time. If you're looking to capture specific rare events, you're going to miss them or certainly undercount them because you're just not going to see them often enough to get a really good idea of what's going on. Okay, so in a lot of these countries then, how do they obtain public health information? Well, what they're really trying to do is to combine data from different sources to complete a picture across both time and space. And we're referring to this procedure of combining data as data amalgamation. So I want to distinguish this between a term called data pooling, which is basically taking the same type of data but from different sources and combining it together. So when I'm talking about combining data from different sources for data amalgamation purposes, I want to take data from surveys, or maybe census data or vital registration data if some countries have them, and combine that with some kind of surveillance system. So there are health and demographic surveillance systems, which are sites that are set up to follow a specific population of people over time, and they collect very detailed information. There are sentinel surveillance systems, which is, there's actually a sentinel in the US right now that is used to monitor adverse health events in post-marketed drugs. There are administrative records, which exist even here, clinical and hospital records. If we're looking at sources in the US, there might be insurance information, and many, many others. So while this seems useful and could be easy enough to do, very, very few people actually do this in practice. And the reason is that there is essentially no conceptual or methodological framework available in order to amalgamate data from different sources in order to produce meaningful results. And that's really the goal of what we're providing today. So we are trying to develop a system that provides high quality, continuously generated, representative vital statistics using a system that is cheap and logistically tractable. So what that means is that it's inexpensive for what you get out of it, and it is easy enough to implement and maintain. So we are going to focus on mortality in young children, aged 0 to 5 years, in the pilot study that I'll talk to you about today. So what we're going to do in our proposed method is take advantage of the benefits of sample surveys, which are really easy to conduct, it's easy to get a representative sample, and it's logistically tractable, with surveillance system, which again provides that detailed linked longitudinal data on people, but it's not necessarily a representative population, and it's usually very, very small. And so we'll combine these sources of data to provide useful indicators for large populations over an extended period of time. So our procedure is called Hyak, which means fast in Chinook jargon. This was one of my collaborators that came up with this, not me. And it has really three components. So there's the data amalgamation component, when the idea for us in our pilot study is going to be capturing as many deaths as possible through our informed sampling procedure. And we want to combine this with a verbal autopsy method to estimate the distribution of deaths at the population level. And then we will also want to try to get at measures of socioeconomic status at the household level. So verbal autopsy, for those who are interested, is basically going back to somebody's next of kin who's been reported dead to find out reasons for their deaths so that you can actually assign a cause of death to a particular event. Okay, so what is our informed sampling scheme like? Okay, so I told you that we want to combine surveys in some way with some surveillance system. So the surveillance systems are the HDSS sites. So they have limited but very good data. And so we want to use this data to say something about what's happening outside of those areas. Which individuals or which households are most likely to be the most informative people, and those are the people we want to sample. Once we do that, we can sample those people with increased frequency, so that increases the efficiency of our sampling and ensures that sufficient data are collected, especially about rare populations. So again, the benefit is that we're fully utilizing that great data that's generated by the HDSS, and then we can subsequently use that data to inform the sampling in the surrounding areas, and then data that's collected on those surrounding areas can then be fed back into the HDSS data collection procedure. Yeah?
When collecting information only from most informative individuals, give a biased view of the data?
Great question. So we can actually take that into account in the modeling step, which comes after. So right now we want to capture people, so it's just a different type of sampling procedure. And then when you think about which models you want to use to actually analyze the data, when you take the design into account, your bias goes away. And I'll show you about that later. Good question. Is there any other questions? Okay. So what our sampling framework looks like. So let's assume that this big blob in the middle is an entire country, and the black lines will denote, say, state borders. The purple blobs will be our HDSS sites, where the size of the blob will reflect the actual size of the HDSS. H here indicates that one of our HDSS sites is a hospital, so it's tracking information on everybody who visits that hospital. So the green dots surrounding all the purple dots are, say, surrounding cities or villages, and those are the ones we want to target to sample and get information from them using knowledge from the purple places. Okay? Okay, so our motivating example comes from a real-world HDSS site in the northeast of South Africa called Agincourt. So it covers an area of about 420 kilometers squared and contains 27 villages. It monitors roughly 90,000 people across 16,000 households. So as you'll see, I'll show you a map in a second, the villages and households are widely dispersed in this area, but there is a road linking them all. There is generally low mortality in the area, with the exception of the HIV effect. And variables that are routinely collected through this HDSS is information on births, deaths, in and out migrations, household relationships, resident and refugee status, education, and then antenatal and delivery health seeking practices. So this is our map of the Agincourt study area. So all of the villages that have red names rather than black names are ones that fall into the HDSS site. So you can see that there are very distinct boundaries for each of the villages, which are highlighted in different colors, and they don't necessarily connect to one another. So if you think about going out and collecting information on a place that looks like this, what would you do to make your life easy? You would probably say, okay, today I'm going to go to Cunningmore A and I'm going to collect 100 households. And then because it's right next door, I'm going to go to Cunningham B and collect another 100 people. And you do it more out of convenience, right? And that's not necessarily bad because you have a limited number of resources. But the problem is that, if you're only collecting, from these 3 villages, it might be hard to say something about what's happening in the rest of an area. Does that make sense? Okay. So what we need to do is translate the Agincourt information into numbers. So the first thing we need to think about is translating the Agincourt data into something useful for me. So what that means is that I will take different probabilities of death, your age and sex breakdown of your children, and I'm going to generate a virtual population based on this information where I know the truth and I control the truth. And then I'll repeatedly sample from this virtual population in order to test out my proposed approach. So along those same lines, you'll think like, how am I going to be able to tell which approach is doing better? Well, we'll need to establish some kind of criteria to talk about sampling approaches that are, quote, better or worse. Now the other tricky part is translating the Agincourt geography into something usable. So what that means is that I want to be able to relate the villages to one another in some way in order to leverage information across villages. So what that means is that if I don't take a sample from every single village, how can I still say something about the other villages in the area? And one way we're going to be able to do this is coming up with a definition for what it means for neighbors to be villages. And we'll talk about why that is important in a few slides. Okay, so now comes the scary notation part. Maybe not scary for you guys because you're mostly math majors, but mostly scary for other people. Okay, so we're going to let I index villages within our study region, and J will index strata. So right now we're going to look at age and sex strata, where we have 2 sexes and 2 ages, young and old, male and female, where old is 1 to 5 years old. It's not old, but anyway, just bear with me. Okay, and then we have households within villages that will be represented by K, and our quantity of interest is denoted by capital YIJ. So that is the unobserved true number of deaths in the village I and age sex stratum J. So this is our target of inference. So I want to make a guess, my best guess, based on my sample at this guy here. And I'm going to assume that I know the total number of people in a village, which is going to be denoted at NIJ. And we'll also assume that we have some kind of village level covariance. We'll denote those by X. So that might be things like socioeconomic status. In South Africa, what might be important is water quality or proximity to a water source. Could also mean proximity to a healthcare facility. Could mean access to some kind of transportation in order to get you to a healthcare facility. Things like that. And then we'll denote little n and little y being the number of sampled individuals and the number of observed deaths in our village I and stratum J. And finally, Pij, which is the probability of death for a given village and stratum. Okay, so now we have to do some modeling. So what does that mean exactly? So we have a binary outcome, alive or dead, and so that means our modeling framework is a logistic regression with random effects, which I'm assuming from my conversation with Peter earlier today, that means nothing to you, and that's fine. So basically, all I want to do is look at the relationship between your alive or dead status and covariates of interest. So this will be, is there an association between your status and your SES in the village? Or between your alive or dead status and your proximity to a water source, something like that. And the way we test those associations is through modeling. So don't worry too much about what that means, just know that I'm doing this. Okay, from the models what we're actually getting is not the number of people who died, but the probability of death. And so how can we then use that in order to obtain an estimate for the population number of deaths? Well, we know that it has to be at least as big as those deaths that we have observed. And how we guess at the remaining number of deaths that we didn't see is through this second piece here. So I just take the number of people that I didn't see, so that's the total number of people in the population minus the number I've sampled, and multiplied it by my estimated probability of death. Okay? And we're gonna get estimates for those probabilities in 2 different ways. So the first way is just a naive model. So if I sample a bunch of people, say 100, and I observe 2 deaths, I might just, even though I've seen people in different age groups and different sexes, and I've seen people in many different villages, I might just say, okay, let's just add everybody together, and I'll say my estimated probability is 2 out of 100. And I'm just going to apply that to every age and sex group and every village, and call it good. That's what we're doing here. In the second approach, we're doing something a little bit more sophisticated, because I want to take into account where you live. So what that means is, I want to know about your village. What do those village characteristics look like? I want to know about your age and sex status in particular. And I also want to know about what villages look like you, and what do their probabilities of death look like. And so this spatial covariate model takes into account all of those things to create a hopefully better picture, or a better guess, at the probability of death. Okay, so that's what the model looks like. That's probably really maybe not what you're used to seeing, so don't worry too much about it. So basically what happens is that we're looking for the association between a probability of death and some covariates, which are denoted by the xi, beta, and the gamma terms. And then we have 3 smoothing terms. So epsilon I and Si are random effects at the village level, which means that we are taking into account similarities between people living within the same village. And then HK is a household level random effect, which allows for dependence within households. So what does that really mean? So if I say, so Peter and I went to the University of Washington, so we have that similarity in common. So that might mean that we behave more similarly in terms of some characteristics than people who went to 2 different universities. So it's the same idea here. So what we're saying with the village level random effects is that 2 people who live in the same place behave more similarly in a way I can't really describe than 2 people who live in places that are very far apart, for instance. Similarly, the H variable basically does the same thing, but at the household level. You are probably more similar to your siblings, assuming you live with each other, than your cousins or even long-distance friends or something like that. Okay, so the SI term is really the interesting one, because that's the one that's going to allow us to smooth across space. And so the model that we're using for that smoothing assumes that the spatial effect in a particular village is more similar to the mean of the spatial effects in neighboring villages, and the strength of that similarity is determined by the actual number of neighbors in a given area. So this is why it's so important in the Agincourt geography to figure out who are neighbors. Okay, so let's go back to our study site. So this is a slightly different map than we had before, but it just basically is focusing on the villages that are falling into the HDSS site. So we've got a bunch of schools, a bunch of clinics, we've got roads connecting places, but it's kind of a weird area. So how would you, does anyone have any ideas about how you might say 2 villages are neighbors or more similar than others? Population size? Size. Sure, that could be one way. But if the population sizes here and here are the same, would you necessarily expect the behavior of their citizens to behave the same? Maybe not. So I'm thinking more in terms of other characteristics that might not be measurable. So you had a suggestion.
I was going to say some sort of graph, maybe.
A graph. Can you expand?
Just so we could know, if one city is further away from another one.
Right. Okay, so distance. Right?
Yeah.
Is that what I'm hearing?
Yeah.
Right. So, good. So that's very standard choice, right? So you can say that if 2 villages are close enough, there'll be neighbors. So, okay, so what I'm suggesting here is based on drawing circles. So what that means is that you take the centroid of every village and you draw a circle of some specified radius around the village. So we'll take this one, we'll draw a big circle of say 50 kilometers. Any village that falls in that circle is a neighbor. Woohoo, we're done. Okay, so that's one way. So another way is to actually form a Voronoi tessellation. Do you guys know what a tessellation is? see some sort of shakes, some sort of nods. Okay, so basically what it is it takes a set of points and it forms a set of tiles based on which points fall closest to your target points or not. So the points in our case are going to be the village centroids, and we want to say, where does all of the other empty space even fall in relation to that centroid, and I'm going to form a boundary. So I'm going to make a set of boundaries between the centroids of the villages to form a partition space so that villages are assigned a much larger geography than is actually represented on the map. Okay? And then once we've got this set of tiles, we can define neighbors as any tiles that touch. Okay, so what does that mean? So if we translate this picture into a set of coordinates, we would just have a bunch of points, right? So that's sort of what this is representing. The map is kind of skewed, but anyway, you get the idea. So each number here represents the centroid of a village number. And the black lines here represent the tiles that arise from the tessellation. So what that means is that all of these points in this tile fall more closely to the number 3 than the number 4, the number 16, or the number 1, which is how we get that boundary. Does that make sense? Okay, so then once we have all of these tiles, we can say, okay, any area, any two tiles that touch, those villages are neighbors. So for village number 2, for instance, it has 5 neighbors. So 2 and 4 share a border, 2 and 18 share a border, 2 and 6, 2 and 13, and 2 and 1. Okay? And what that also means is that if 2 is a neighbor of 1, 1 is a neighbor of 2. This is a mutual street. Okay. Okay, so now that we've got our models, we've talked a little bit about geography, how do we sample the people? Okay, so remember back to the beginning of the talk, I said if you had limited resources and you had a bunch of spread out villages, how would you sample people? So you might go and you might say, okay, I can only take 5 villages, and I'm going to go into those villages and I'm going to randomly sample a bunch of households. Maybe you'll take like a couple of city blocks and you'll interview everybody in every household on those city blocks. So that's commonly what's done, and that is referred to as a 2-stage cluster sampling. So the first stage involves selecting the villages, the second stage is selecting the households. So in our informed sampling procedure, we say, okay, I want to sample the kids in the villages proportionate to how many predicted deaths I expect. So using the HDSS data, I'm going to create a model for the association between village level covariates and the probability of death, and I'm going to extrapolate to all villages in my study area to be able to get a prediction for the probability of death and then subsequently the counts in each area. And I'm just going to sample proportionately. So that means if I think that your village has more deaths, I'm going to sample you more heavily. Okay, so our pilot study procedure. So what does this mean? So I am going to create 2 virtual populations, one that I'll use to get the HDSS data from, and the other one will be the one we're sampling from. So I'm assuming we only have 20 villages to simplify things a little bit. We'll assume that we have between 1,400 and 14,000 children in each village with a roughly 50-50 split between boys and girls, and only a fifth in the 0 to 1 age range. Households can contain between 1 and 5 children in our virtual population, and about a third of the households will contain 3 kids. And then what we're going to do is repeatedly draw from this virtual population to create samples, and we'll fit our models and measure how well we do in terms of getting good guesses at the number of deaths in given areas in given strata. Okay, so how do we evaluate whether or not we're making good guesses? So there is the notion of accuracy and precision. Have you guys seen this? I don't want to belabor the point if you've looked at this already. Okay, so we know that you can be highly precise and very inaccurate, and vice versa. So the goal is obviously to live here, right? Highly accurate, highly precise. We can't always get that. In statistics, our notion of accuracy and prediction falls, and precision falls into the terms bias and variance. Do you guys know what bias and variance are? Right, okay, great. So we're going to be using the criteria called the mean squared error to evaluate how well we're doing. We want a small mean squared error, and it's composed of bias squared plus the variance. So that means if we have So we'll have a balance between bias and variance, and as long as that balance results in a roughly small MSCE, we're good to go. Okay, so here is a table of results. So we've got two designs, cluster and Hyak. We've got two models, the naive model and the spatial model. And then I'm showing you here the mean number of deaths that we've captured across the 100 draws from our population, as well as the bias, variance, and MSE. So what do we notice straight off the bat? Well, our goal was to collect more deaths, and our informed sampling procedure does do that. And that's good. We've sort of designed it that way so it passes the smell test. That's good. Okay, so now if we look within the Hyak rows of the table, we see that when we combine the informed sampling procedure with a model that smooths across space, we are doing so much better in terms of our predictive accuracy. So you can see that our bias is an order of magnitude smaller using the spatial model, but we lose a little bit on the variance. So that's the bias-variance trade-off. And you'll notice that we weren't able to fit the spatial model in the cluster sample because the model that we use requires at least one sample person per village. Don't worry about those details. We didn't go into enough detail to talk about that some more. Okay, so this is an example of the results across 100 simulations for our Hyak sampling procedure for one particular village. So this is the probability of death in each of the four stratum, and we're comparing the naive model, which are the triangles, to the spatial model, which have the X's. So what you can see is that the naive model produces very precise measurements, but they're not very accurate because they're not often capturing the truth, which are represented by the red bars. Whereas the spatial model has slightly more variability. You can see that in the range of the X values, but it's capturing the truth every single time. So that gets at the idea of the bias-variance trade-off. So we're willing to lose a little bit on bias to get we're willing to lose a little bit in variance to gain in bias. Okay, so in the last couple of minutes, basically what I've hopefully showed you here today is that combining highly informative data produced by something like an HDSS site can be used to judiciously sample a large surrounding area to get estimated counts that are more useful, meaning lower MSE, than traditional cluster sampling design. And further, if we combine that with a model that smooths over space, we're doing a heck of a lot better. But the crucial idea here is that the very detailed information collected from our HDSS site can be extrapolated meaningfully to the larger surrounding area. And what that really means is that the population being monitored by the HDSS site has to be similar or representative in some way in terms of the relationships being studied to the surrounding area. That might be true, but it might not also be true depending on the situation that you're studying. So the key advantage that we were trying to get at with Hyak is that it's capturing significantly more deaths. So why might this be important? Well, tying it back to the beginning, we said that verbal autopsy methods can be used to estimate, to assign causes of death to maybe all, maybe just some, depending on resources of the deaths that you collect. So why might this be important? Well, if you construct the distributions of deaths by cause over time, you can actually illustrate the epidemiology of the population and see how it's changing over time, which would be important especially for also measuring impacts of interventions, which is being done all the time. So this is really just a very small snapshot into a very small pilot study. So how can we think about taking this to the next step? Well, there's a lot of things that we need to consider. So one question that we didn't even come close to addressing is how large do these HDSS sites need to be in order to provide enough information for effective informative sampling? How many of these sites are needed? How should we disperse them geographically? If we want to get more fine-grained estimates by specific key indicators, how well does it work in that case? We didn't even look at that. How inexpensive is it really? We need to do some kind of costing analysis to figure out if this approach of sampling from all villages is really going to be cost-effective and feasible. And then most importantly is how can we scale this up to a much larger geographical area, given our toy example was very small in geography and a very small number of villages. So I'd just like to take a couple seconds to acknowledge my collaborators. John Wakefield was my dissertation advisor at University of Washington. He is joint professor in biostat and stat there. And then Samuel Clark and Tyler McCormack are both in sociology. Sam is a professor, Tyler is associate professor, and Tyler also has a joint appointment in statistics there. And that's it.